Okay, I'm going to do a demonstration of electromagnetic induction. If you remember before, this coil, I brought this to class one day and hooked it up to this power supply, ran a current through it, and you saw that it created a magnetic field inside. Well, now I have it hooked up to a galvanometer, which can measure very small currents. So when there's no current, the needle is at the zero position straight up. When current's in one direction, it deflects to the right. And if the current is in the opposite direction, it deflects to the left. And now here I have a magnet with a north pole and a south pole. Now watch the needle when I push the north pole into the coil. It deflects, right? But then it went back to zero. If I just hold the magnet inside the coil, there's no change in the magnetic field. But while the magnet is moving, there's a changing magnetic field in the coil, which induces a current in the coil, and that shows up on the galvanometer. So I push the north pole in, it deflects one way. I pull the north pole out, it deflects in the opposite direction. So Lenz's law tells us that the induced current is in the direction to oppose the change. So when I push the north pole in, the current goes in a way to create a north pole up to push against me. When I pull the north pole out, the current reverses the direction to make a south pole up to try to pull the magnet back in to oppose the change. But as long as the magnet is moving, I have a current, right? So just moving the magnet in and out, I'm creating an alternating current. See, it goes back and forth. But of course the magnet has to be moving. If it's still, there's no change in the magnetic field, and it doesn't move. So the magnet has to be moving to create a current. Okay, now I have my little electric motor, and I brought this to class too and demonstrated this before. My armature consists of a coil with copper wire wrapped around it, creating the coil, and I have two bar magnets to create the magnetic field. Up here at the top I have my split ring commutator. Here's the brushes to make contact with the power supply. And so if I turn on the power supply, I have an electric motor. So it spins, right? So I input an electrical current in, I get out mechanical energy in the form of spinning armature. So I'm converting electrical energy into mechanical energy. I input electrical energy and I get out mechanical energy to spinning of the armature. So now what happens? I'm going to turn this off, disconnect it from the power supply, and now I'm going to hook it up to the galvanometer. So I connect the leads to the galvanometer. Now this time I'm going to reach in here and I'm going to spin the coil by hand. And now watch what happens when I spin the coil. Whoa, see that? The needle deflects. I can even peg the needle. So what's going on? I'm creating current. So instead of a motor, I have a generator. I'm inputting mechanical energy. I'm mechanically spinning the armature. And by spinning the armature, I get out electrical energy in the form of an electric current. So my motor is now a generator. So this demonstrates that a motor and a generator are the same device. It's just how it's operated. As a generator, I input mechanical energy and I get out electrical energy in the form of electric current. For the motor, I input electrical energy and I get out mechanical energy in the form of the spinning armature. But in both cases, they're the same device. Okay? So as the armature spins, it generates a voltage in every loop of the coil. So Faraday's law tells us I get an induced voltage in every loop. The more loops I have, the greater the induced voltage. The faster this spins, the greater the induced voltage as well. Because as it spins, I have a changing magnetic field through the coil. That changing magnetic field induces a voltage in the coil, and since I have a complete circuit, I get an induced current. Now, a curious thing about this is that even when I operate it as a motor, I still get the induced voltage due to the spinning of the armature. I still have a coil with a changing magnetic field in it as the armature spins. And that induced EMF is in the opposite polarity of the line voltage that drives the motor. That occurs in all electric motors. So as the motor spins, the faster it spins, the greater that induced voltage. We call that a back EMF. The back EMF is the voltage due to the spinning of the coil. That's that induced voltage due to the spinning of the coil. The faster it spins, the greater the back EMF. And the back EMF is in the opposite polarity of the line voltage that drives us. So the faster the motor spins, the smaller the net voltage is for the motor. Okay? And again, that occurs in all motors. So when you first turn on the motor, it's not spinning yet. So the only voltage we have is the line voltage. And so we get a large current when the motor starts up. But as soon as it starts to spin, well, then the back EMF drops the net voltage down because the back EMF is opposing the line voltage. And so that has the effect of limiting the speed of the current. So as it gets faster, the net voltage decreases, the current decreases, and then it reaches a steady state, and it cannot spin any faster than that. So what happens if I overload the motor? If I overload the motor, now I've slowed the motor down. If I slow the motor down, the back EMF gets smaller, and then the line voltage will dominate, and it draws more current, which wants to make it spin faster. So I'm supplying more energy to try to drive the load that I put on the motor. Okay. So that occurs because of the back EMF. This also occurs, you may have noticed in your central air conditioning in your house at home. When the central air conditioning first kicks on, you ever notice the lights might flicker a little bit, just momentarily when it first turns on. Well, what happens is your central air conditioning has a very large electric motor to run the compressor. And when it first turns on, it's not spinning yet, so it draws a huge amount of current for the startup. But then as soon as the motor starts to spin, then the back EMF gets larger, and the net voltage gets smaller, and then the current drops down to its steady operating value. But that instant startup current is very, very large, can be 10, 15 times larger than its normal operating current. And so that's why you get that little flicker in the lights because of that. Okay, now I have a little generator, hand crank generator, and if you look inside, you can see a silver cylinder inside. That's actually a little electric motor like you might find in a battery-powered toy, like a toy car or something like that. We're going to operate it as a generator. So it's the shaft of the armature is connected through gears to the crank, and then I spin the crank, I'm spinning the little electric motor and making it a generator. So I can hook it up to this light bulbs. And now as I crank it, you can see the lights go. The faster I spin it, the more current I get, the brighter the bulbs. I turn it slow, the bulbs are bright again. But also when I spin it, I can feel a resistance because of the current through the coil creates a back EMF. Right? And I can feel that resistance. As soon as I disconnect one and I no longer have a current through the motor, I can easily spin that. There's hardly any resistance to it. But as soon as I hook it up and try to spin it to generate a current, now I get a resistance. See? Now remember, we had said that a motor and a generator were the same device. So I have a second one over here. My assistant, would you hold this, please? Hold the handle so this can move. I'm going to connect one thing to the other. Okay. Now I'm going to crank this and watch what happens to that. So I'm operating this one as a generator to produce a current to make that one run as a motor. And if I turn the other direction, it goes the other way. Okay, you spin yours. Okay, hold it still now. Now, watch what happens. I'm going to turn this one complete turn and watch how far this one moves. It started from here and went over here, so it only went about 2/3 of the way, didn't it? One turn here gives me about 2/3 of a turn there. So why is that? Well, of course, some of my input energy is converted into heat because of the friction in the coil, and also there's some resistance in the wire that generates heat. So I get some loss of my input energy, and that's why I don't get 100% of it transferred. Okay. But again, you can see how a motor and a generator are the same device.